Hello, in this video I will be showing you how to do mathematical induction. Mathematical induction is used to prove something for all or some integer values n. You start by proving that it is true when n equals 1, and after that you prove that if it is true when n equals k, it also must be true for when n equals k plus 1. Now I will show you some examples. Prove that 2n minus 1 is always odd for all integers n. When n is equal to 1, 2n minus 1 is equal to 1, and 1 is odd. Therefore, our base case is true. When n is equal to k, 2n minus 1 is equal to 2k minus 1, and when n is equal to k plus 1, 2n minus 1 is equal to 2k minus 1 plus 2, so our value for when n is k plus 1 is 2 more than our value for when n is equal to k. Since adding 2 to a number does not change its parity, if 2n minus 1 is odd when n is k, 2n minus 1 must also be odd when n is k plus 1. Therefore, 2n minus 1 is odd for all integers n. Now I will show you another example. Prove that phi to the power of n plus 2 is equal to phi to the power of n plus 1 plus phi to the power of n for all integers n. Phi is a number that is equal to 1 plus the square root of 5 over 2. When n is equal to 1, or the base case, phi to the power of n plus 2 is equal to 2 plus the square root of 5, and phi to the power of n plus 1 plus phi to the power of n is also equal to 2 plus the square root of 5. Therefore, our base case is true. If we assume that it is true when n is equal to k, then phi to the power of k plus 2 would equal to phi to the power of k plus 1 plus phi to the power of k. And if it were to be true when n is equal to k plus 1, then phi to the power of k plus 3 it would equal to phi to the power of k plus 2 plus phi to the power of k plus 1. This simplifies down to what we had before for when n is equal to k. Phi to the power of k plus 2 is equal to phi to the power of k plus 1 plus phi to the power of k. Therefore, if phi to the power of n plus 2 is equal to phi to the power of n plus 1 plus phi to the power of n is true when n equals k, then it is also true when n equals k plus 1. Therefore, phi to the power of n plus 2 is equal to phi to the power of n plus 1 plus phi to the power of n for all integers n. Now I will show you 3 problems for you to work on yourselves. Problem number 1. Prove that 5 to the power of n minus 1 is even for all integers n. Problem number 2. Prove that n cubed plus 2n is divisible by 3 for all integers n. Problem number 3. Prove that the series 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed is equal to 1 plus 2 plus 3 all the way to n squared for all integers n. Thanks for watching, and please stay tuned to my next video where I show you the answers to the 3 problems displayed.